Hi everyone, welcome to another session of the HBL files. Today we will be solving problems about measurements and uncertainties. This will include estimation, significant figures, precision and accuracy, vectors, and scalars. Let's begin with the multiple choice questions. For the first question, the magnitude of the mass of the universe is of the order of. Take note that we are talking about the universe. The universe has lots of galaxies in it. Each galaxy will contain lots of stars, and each of those stars may have planets revolving around them. Now, the planets may also have moons revolving around them. And not to mention, we also have comets and asteroids. So for this question, the most likely answer will be letter D, the biggest mass given among the choices, which is 10 raised to 50 kilograms. Next question, which of the following is a valid statement? This question pertains to the idea of precision and accuracy. Remember that being precise means that the values that you've obtained have little variations, meaning the range of the values is small. On the other hand, being accurate means that your measurement is close to the true value that is accepted or the standard value for that quantity. If you look at letter D, repeated measurements will always increase accuracy and precision. This is not true. Why? Because even if you repeat your measurements, but then the instrument you're using has a zero error, that means all your measurements will always have that error. So this option is not true. Next, if you look at letter C, a measurement that is not precise will always be inaccurate. This one is also not true. Why? Because there are cases wherein even though the measurements are not precise, meaning the measurements are far from each other, meaning their values have larger differences or large differences, if we get their average value or average distribution, it's possible to get an average value that is close to the true value, which is being accurate. Letter B, on the other hand, a measurement that is precise is always accurate. Again, this is not necessarily the case because you can be precise but inaccurate, just like the one being shown in letter D. If you have a zero error, your measurements may be close to each other but not to the true value. And if we go to letter A, a measurement that is not precise can be accurate. This is somewhat related to letter C. Again, if we consider the average values of those measurements, it is possible that it's close to the true value. That means for this question, letter A is the answer. Next, in an experiment to measure the acceleration of free fall at the surface of the Earth, the following results were obtained. The results are, so again, this is a question about precision and accuracy. Note that the acceleration of free fall should have a value of around 9.81 meters per second squared. Looking at the values, the range of the values will be just around 0.02. The highest value is 7.70, the smallest is 7.68. So there's not much variation among the given values. That means the values are precise. They are close to each other. But if you look at these values and the value of acceleration of free fall, take note that these values were not close to this value. So that means the values obtained were not accurate. For this question, the answer will be letter B, inaccurate but precise. Next, the length of each side of a sugar cube is measured as 10 millimeters with an uncertainty of plus minus 2 millimeters. Which of the following is the absolute uncertainty in the volume of the sugar cube? Remember that the formula for volume of a cube is V is equal to S cubed, where S is the length of one side. Solving for the volume of the sugar cube will have 1,000 cubic millimeters. Now, for the fractional uncertainty of the side, or the length of the side, we know that the absolute uncertainty is 2, while the measurement of the side is 10. This gives us a fractional uncertainty of 0.2 for the length of one side of the sugar cube. Now, to determine the fractional uncertainty in the volume, we must multiply the fractional uncertainty of the side of the cube to 3. Why? If you look at this formula, notice that S was raised to 3. That means we will be using S as a factor for 3 times. So that's S times S times S. Remember that when we are multiplying quantities with uncertainties, we tend to add their fractional or percentage uncertainties. So since we have the same uncertainty added for, so we'll be using this fractional uncertainty for 3 times, we can just simply multiply this fractional uncertainty by 3, giving us 3 times 0.2, which is equal to 0.6. We now have the fractional uncertainty of the volume to be equal to 0.6. Remember that we are asked for the absolute uncertainty in the volume, which is represented by this variable. So to solve for the absolute uncertainty, we then multiply the volume to 0.6. We know that the volume is 1,000 cubic millimeters. So substituting that one, we'll have the value of the absolute uncertainty in the volume to be equal to 600 cubic millimeters. That means the answer for this question is letter D, plus minus 600 cubic millimeters. Next. The current in a resistor is measured as 2 amperes plus minus 0.02 amperes. Which of the following correctly identifies the absolute uncertainty and the percentage uncertainty in the current? Take note that the main difference between absolute uncertainty and percentage uncertainty, or fractional uncertainty, is that absolute uncertainty has a unit. Notice that in this measurement, the 0.02 or the plus minus 0.02 has a unit of amperes. That means this is the absolute uncertainty. Looking at the choices, we only have option A and option C to indicate that value for the absolute uncertainty. Next, we'll then compute for the percentage uncertainty. How do we do that? We get the fractional uncertainty in current and then multiply it by 100. The absolute uncertainty is 0.02, and then the value of the current is 2. Dividing this and multiplying it to 100 gives us 1%. That means the answer for this question is letter A. Next, which of the following lists only 2 vector quantities? So again, when you talk about a scalar quantity, it requires magnitude only. On the other hand, if we have a vector quantity, it requires both the magnitude and direction. So the measurement plus where is that measurement going to? Now, looking at option A, mass is scalar, energy is also scalar, work is scalar. On letter B, momentum is a vector, work is scalar, speed is scalar. On letter C, weight, force, and acceleration are all vectors. That means the answer for this question is letter D, where momentum is a vector quantity, energy is a scalar, displacement is vector. Next, Samantha walks along a horizontal path in the direction shown. So from P going to Q. The curved path of the curved part of the path is a semicircle, this part over here. The magnitude of her displacement from point P to point Q is approximately, okay? So let's look at this part of the figure. This is a semicircle. That means this 2 meters is actually the radius of this semicircle. So this will be the diameter, which is twice the radius, giving us 4 meters. Since we're only asked for the magnitude of the displacement, we just have to add these lengths, giving us an answer of 8 meters. Next, an object falls for a time of 0.25 seconds. The acceleration of free fall is 9.81 meters per second squared. The displacement is calculated. Which of the following gives the correct number of significant digits for the calculated value of the displacement of the object? For this question, you might want to recall the equations of motion, which are the following. Notice that in this question, it says that the displacement is calculated. So only equations 2, 3, and 4 will contain the displacement variable. But then you are also given with time and acceleration. Now, only equation 2 involves time and acceleration in its equation. So if you are solving for the displacement, notice that you are multiplying acceleration to the square of the time. Remember that when we are multiplying or dividing quantities and we need to follow the number of significant figures in our answer, that means we will be using the least amount of significant figures among the factors that we have used, or among the numbers that we have multiplied or divided. Notice that the time is given to be 0.25 seconds. This will be equivalent to 2 significant figures. On the other hand, the acceleration has 3 significant figures. So here the process is multiplication. So our final answer should have the least number of significant figures among the things that or variables we have multiplied, which means the answer to this question will be letter B. The displacement of the object will have 2 significant figures. Okay, let's now move on to the problem solving. First question, a boat travels at 2 meters per second east towards a port 2.2 kilometers away. When the boat reaches the port, the passengers travel in a car due north for 15 minutes at 60 kilometers per hour. And then we are asked to calculate these quantities. Let's begin by illustrating the problem. So we have a boat that travels 2 meters east. Okay, so speed. This is the direction of the travel. This is the distance. And then this is the port. When the boat reaches the port, the passengers travel in a car due north. Okay, so they'll transfer to a car, travel north for 15 minutes, and then for 60 kilometers per hour. Okay, so for the first question, calculate the total distance traveled. For the first part of this travel, we know that the distance from their initial position going to the port is 2.2 kilometers or 2,200 meters. We then have to determine the distance traveled for the second part when they were riding the car. So we'll just be using this equation. Speed is equal to distance over time. Distance is simply the product of speed times time. Since the speed was given in kilometers per hour and the time was given in minutes, let us convert this R, this unit, into minutes, giving us 60 times 15 divided by 60, or simply 15 kilometers, or in meters, that's 15,000 meters. So to get the total distance, we'll just be adding the two distances, giving us a final value of 17,200 meters. That will be the total distance traveled. So next question will be the total displacement. So since we're asked for the displacement, let's make use of a vector diagram. So this arrow represents this displacement of 2,200 meters to the east. And then that's the port. And then this will be the displacement when they are in the car. This will be equivalent to a displacement of 15,000 meters going north. So the total displacement will be from the initial position going to the final position, and that will be represented by this arrow. Okay, so to compute for the total displacement, we'll make use of the Pythagorean theorem. Since we have this triangle over here, and take note that all of the sides are pertaining to this or to similar quantities, which are displacements. So we have 2,200 squared plus 15,000 squared. Solving this one, we'll obtain a value of 15,160 meters. That means the magnitude of this total displacement will be 15,160 meters. Now, since displacement is a vector quantity, therefore we need to determine the angle for its direction. Okay? Now, the angle that we'll be considering will be this angle over here between this total displacement and the displacement of 2,200 meters. Now, considering that angle, we'll have the following computation. If the angle is measured from this point, this side will be the opposite and this will be the adjacent, meaning we can use tangent theta. Since we are solving for the angle, we'll get the arctangent of the quotient of opposite over adjacent. We'll now have the following values. So evaluating this equation, we'll now have 82 degrees north of east. Now, how do we determine this part of the answer? North of east, east of north, west of south. Okay. Now, notice that this is our reference direction, north, south, east, and west. When measuring an angle, we start with the part or the side where it lies on one of these directions. In this situation, it's this part. This corresponds to east. Now, we then go this way to trace this angle. So going this way corresponds to going from this point to north, which means we went to north from east, or simply 82 degrees north of east, where you're going and where you started. Okay? So the complete answer for this one is that the total displacement will be 15,160 meters at 82 degrees north of east. We write it or we answer it this way because displacement is a vector quantity. Next, the total time taken. To solve for the total time taken, we again make use of this illustration that we have used in solving letter A for this question. Notice that I've added the distance for this part of the travel. So here we know that the time it took them when they're traveling using the car is 15 minutes, or 900 seconds. We then just have to solve the time it took them when they were traveling towards the port. So again, we'll make use of this equation. Speed is equal to distance over time. Solving for time, we have distance over speed. So distance is 2,200 meters and the speed is 2 meters per second. Again, you just have to make sure that your units are consistent. This gives us a final value for the time to be equal to 1,100 seconds. So solving for the total time in this whole journey, we have 900 plus 1,100, which gives us 2,000 seconds. Next, we are asked to calculate the average speed in meters per second. So to calculate for the average speed, we just have to determine the total distance and divide it by the total time. Notice that we already know the total distance and the total time. The total distance we calculated in letter A was 17,200 meters, while the total time that we calculated in C is 2,000 seconds. This gives us a value of 8.6 meters per second for the average speed. And lastly, we have the magnitude of the average velocity. So to compute for the average velocity, just get the total displacement over the total time. Total displacement is just 15,160 meters. Divide that by the total time, which is still 2,000 seconds. This gives us a value of 7.6 meters per second for the average velocity. So take note of the difference when you're computing for average speed and average velocity. Since speed is a scalar quantity, we are making use of distance. On the other hand, since velocity is a vector quantity, we should use the displacement. Now, we don't have to calculate for the angle anymore since we are only asked for the magnitude of the average velocity. But actually, if you'll be computing for the angle, you'll see that the angle is a value that you have already computed in the previous part of the question. Next question. A river flows from west to east with a constant velocity of 1 meter per second. A boat leaves the south bank heading due north at 2.40 meters per second. Find the resultant velocity of the boat. Again, let's illustrate the problem. Say, for example, this is the river, and then the river flows this way from west to east, okay? And then the boat leaves the south bank. This is the south bank, heading due north. So the direction of the movement of the boat will be due north. Now, let us make a representation of the vectors in this scenario. First is the river flow, which is in this direction, given this speed of speed of 1.0 meters per second. And then for the boat, it will be due north with this speed 2.4 meters per second. So to find the resultant velocity of the boat, we must start from the initial position, this part, or the tail of the first vector, and then connect that to the tip of the second vector, which is like this. This arrow over here represents the resultant velocity of the boat. Okay, since velocity is a vector quantity, then we'll be solving for both the magnitude and the direction. So for the magnitude, we again make use of the Pythagorean theorem, substituting the given values and solving for the magnitude of this velocity. We'll have 2.6 meters per second. Now, if we consider again this angle over here, notice that this side is opposite and this is adjacent, giving us or allowing us to use tangent theta. Now, just one tip, guys. Remember that when you're using a triangle of vectors like this, make sure that all of these vectors, all of the arrows, will represent the same or similar quantities. Meaning, if one arrow represents velocity, the other arrows should represent velocity as well. If one arrow represents force, the other arrows must represent force as well. If, say, for example, one is acceleration and then this is velocity, automatically you cannot solve the problem using this. Because, again, the quantities that you should use when using this method should be similar quantities. Okay, so going back to this part, solving for the angle, we have the arctangent of opposite over adjacent. Substituting the given values, we'll obtain 67 degrees north of east. So remember that when we measure the angle, we start with the side where a side that lies along the north, south, east, west direction, which is in this case this one. And then to trace this angle, we went this way. So that's basically going to north from east. So 67 degrees north of east. Again, this is where you're going and then where you started. Okay. So the resultant velocity of the boat in this example will be 2.6 meters per second at 67 degrees north of east. Next problem. A plane has an airspeed of 500 kilometers per hour due north. A wind blows at 100 kilometers per hour from east to west. Draw a vector diagram to calculate the resultant velocity of the plane. Give the direction of travel of the plane with respect to north. Okay, so let's illustrate the problem. This is the representation for the velocity of the plane, okay, with the magnitude 500 kilometers per hour. This is the orientation because the plane was traveling due north. Next, for the wind, it will be like this. Why? Because it says here that the wind is blowing from east going to west with this velocity of magnitude 100 kilometers per hour. So to determine the direction of travel of the plane and the resultant velocity of the plane, we draw a resultant vector from the initial position going to the final position, or from the tail of the first vector to the tip of the second vector, which is this one. Now, since we are asked for both magnitude and direction, let's first solve the magnitude using the Pythagorean theorem. Substituting the given values, we'll obtain 510 kilometers per hour as the magnitude of the resultant velocity. Next, for the direction, we'll be making use of this angle since it was mentioned in the problem that the angle should be with respect to the north, and this is the north direction. So again, notice that when using this angle, this is side opposite, this is side adjacent. Let's make use again of tangent theta. Solving for theta, we have the arctangent of opposite over adjacent. And then substituting the given values, opposite is 100, adjacent is 500. This gives us a value for theta that is equal to 11 degrees west of north. So why west of north? Again, we started with this direction, which is north. We went to this direction to trace this angle. And that's west. So going to west from north. That means the resultant velocity of the plane will be 510 kilometers per hour at 11 degrees west of north. Next question. The diagram shows three forces, P, Q, and R, in equilibrium. P acts horizontally and Q vertically. When P is equal to 5 newtons and Q is equal to 3 newtons, calculate the magnitude and direction of R. So notice that in this problem, it mentioned that the forces are in equilibrium, okay? And there are three forces acting. So copying these forces, we have the following: P, Q, and R. Now, when we have a situation like this, wherein we have three forces and the situation is in equilibrium, or the forces are in equilibrium, we can actually draw this triangle of forces over here, copying the directions of each of the force. So P is in this direction. We then put the Q over here. So the tail of Q is at the tip of P. Following the same method, we have R, tail of R at the tip of Q. Notice that, again, in this triangle of forces, all the sides are pertaining to forces, and we again have a right triangle. Now, to solve for the magnitude of R, we again make use of the Pythagorean theorem. Since R is the hypotenuse, we'll be solving for C. This gives us a value of 5.8 newtons. Now, as for the direction, we will again make use of an angle. Now, take note that when determining the direction of R, we must be very careful as to where we are gonna measure the angle. When we want to determine the angle or the direction of a vector, we must make sure that the angle we are drawing is at the tail of the vector. So we'll make use of this reference coordinate system, and then we can make use of this angle over here. So if you look at this angle, side opposite to it will be Q, side adjacent to it will be P, because the angle over here and this one are basically the same. Solving for the angle, we have arctangent of Q over P. Substituting the given values and evaluating this, we'll obtain 31 degrees north of west. Why north of west? Because again, we start at a side where it lies along one of the directions, north, south, east, west. So that means this side, which is west. And then to trace this angle, we go this way, going to north. So 31 degrees north of west. That means the magnitude and direction of R in this example or in this question will be 5.8 newtons at 31 degrees north of west. Next question. A car of mass 850 kilograms rests on a slope at 25 degrees to the horizontal. Calculate the magnitude of the component of the car's weight which acts parallel to the slope. So let's illustrate the given problem. This is the ground level. This is the slope at 25 degrees from the horizontal. This is the car. And the car's weight is drawn vertically down. Okay. Now, let's copy the weight and let's just enlarge it. So again, this is the weight. This is the slope over here. And then this will be our coordinate system, which is tilted. This is the x-axis, which follows the slope. And then perpendicular to it will be the y-axis. Notice that the weight is at an angle with respect to the y-axis and x-axis. That means we can determine its components. The y component will be this one, and this is the x component, or the component along the slope. Now, copying this vector for the weight and its components, we'll have this one. This is actually also 25 degrees by carefully studying this diagram. And this one is 90 degrees. Notice that the x component in this figure was moved here to form this right triangle. Now, continuing the solution, we can actually use sine theta to solve for the component of the car's weight along the slope. Why? In this problem, we are supposed to compute for this. If we'll be using 25 degrees, this side is actually opposite to 25 degrees. And we know that this is the weight. We can actually compute it since we're given with the mass. So let's use sine theta. Opposite side is the x component of the weight, while the hypotenuse is, of course, the weight itself. Manipulating this equation, we have Wx is equal to W sine theta. And then substituting the values, weight will be mass times gravity, so mass of 850 kilograms, and gravity will be 9.81 meters per second squared, of course. Then theta will be 25 degrees. Solving this, we'll obtain 3,524 newtons, or approximately 3,500 newtons for the component of the car's weight that is parallel to the slope. Okay, so that's it, guys. Thank you for learning with me today. And please subscribe to my channel for more physics tutorial videos. See you on the next session of the HBL Files.